Hello everyone, welcome back to the How series. We are beginning session 7 of the workshop Programming and Optimization for Intel Architecture. Today's session is one of the key sessions in Module 3 where we discuss performance optimization. We are going to talk about scalar tuning and about the optimization of vectorized calculations. A reminder for everyone, we have a course web page where you can download my slides. Slides, by the way, have clickable links, and you can also download code there. We have video recordings of all sessions, and you can ask questions in the chat as I speak. Please navigate to this page now to join the chat. The chat window is at the very bottom of the page. Feel free to type as I speak. We will take care of the questions as they come in. If you want to ask questions offline, or if your questions require an extended answer, we have Colfax Research forums. Feel free to post there. This is a hands-on workshop. I will be demonstrating what I teach using programming exercises and the Colfax cluster with a Xeon processor and Intel Xeon 5 co-processors and processors. You have access to this cluster as well. When you register for the webinar, you should receive an invitation. Have not received an invitation yet? Please check your spam folder, and if it's not there, write us a message. You can use the cluster not just during the presentations, but for the entire 2 weeks of the workshop. When we talk about performance optimization, we are going to target the platforms that we have in the cluster, Xeon and Xeon Phi. But once again, my goal is to show you not how to tune for a particular platform, but how to program in such a way that your application is aware of the fundamental building blocks, and therefore you can design a single code that will be portable across existing platforms and also future-proof, ready for the upcoming generations of Intel processors and Intel-like processors. To accomplish that, we structure all optimization topics into 4 areas of node optimization and 1 area of cluster level optimization. Today is a focus session where we will discuss techniques specific to scalar tuning and the optimization of vector calculations. First, we will talk about scalar tuning, and the way I see it, it has 2 sides: interacting with the compiler, interaction with compiler, and programming practices. Scalar tuning refers to all of the techniques that allow you to improve the performance of your application without touching the vector aspect or the multi-core aspect of your calculations. First, we will talk about interactions with the compiler. In this course, we focus on Intel compilers, and so what I show is going to be specific to this compiler family. The primary compiler argument that you should be aware of is the optimization level setting, -O followed by a number, 0, 1, 2, 3, or S for small code. What you should know here is that the default optimization level is O2, and it is actually fairly aggressive with respect to optimization. I will show you which optimizations it includes in a minute. It includes, among other things, automatic vectorization. You should also be aware of -G. -G embeds debugging symbols in your code, and this is useful for debugging, and also it is useful for performance profiling with a tool such as vtune. If you go the vtune route, you need to use -G, but then you need to be aware that -G disables all of the optimizations of O2 and resets optimization to O0. It is actually possible to set it back. So when you go with vtune, generally you will use a combination -G, -O2, or O3. I will also talk a little bit about the floating point semantics setting. And again, I want to let you know that Intel compilers are actually designed to implement relaxed semantics for floating point expressions by default, fast equals 1. If you want to go for the fastest floating point semantics, use fast equals 2, and there's also strict and precise if you want, say, compatibility with floating point mathematics standards, such as IEEE 754. FIMF precision, this is an argument very much related to optimization. It sets the precision of transcendental functions in the Intel Math library. We also talked about -x followed by the code name of the architecture. We talked about it in session 3. It allows you to target a particular processor. And to do code dispatch for multiple architectures, you have AX. I have not mentioned, and unfortunately I don't have time to talk about interprocedural optimization. But if you use this argument, Intel compiler will build very thick object files, which will allow it to do advanced optimization at the link stage. And it really makes compilation longer, but you may get better optimized code. By the way, all of the arguments that I'm showing here, see green, all of these links are clickable. And if you wish, you can go and click, and it will take you to the Intel C++ compiler user and reference guide. Fortran compilers have similar or very much the same arguments. I want to zoom in a little bit on the optimization level argument. By default, Intel compilers use O2, optimizing for speed, sometimes at the cost of precision. Automatic vectorization is enabled, and standard techniques for optimization, such as inlining, custom propagation, dead code elimination, loop enrolling, all of this is enabled. O3 is even more aggressive with additional settings. What I want to stress in this slide is that O3 is not necessarily better than O2. For example, if you look in the n-body simulation that we discussed yesterday, and you see a solution for instruction 4, it is compiled with O2. Compile it with O3, and you will get worse results on Knights Landing processors. This is because, in that particular case, O3 overrides my unroll settings, and I happen to pick a better unroll factor than the compiler does. So, if you need to tune the optimization level, you might consider tuning it on the file level. So if you compile a file with O3, and some of the files need to be compiled with O2, definitely you can do that. Something that you may want to learn is this. There is a directive that resets the optimization level for just one function. So if you see that just one function requires an optimization level different from the rest of the project, you can use the directive. The other side of scalar tuning is programming practices that you should use to maximize your performance. In session 6 yesterday, we talked about strength reduction. Strength reduction is the name for programming techniques that replace arithmetic operations with approximately equivalent but faster arithmetic operations. There is a very well-known example of strength reduction where you take a division by the same number over and over, and you replace it with multiplication by the reciprocal of that number. It is well known that multiplication in computer architectures is typically much, much faster than division. Indeed, I will show you the slide that lists the latencies and throughputs. So this is going to be faster. It's going to be faster, but you might lose accuracy by doing that. So you need to evaluate every time that you do this, is it worth it or not? There is a common misconception that you should never do that, and the compiler will take care of that. You will see several examples proving that this is false. the compiler will often not make this replacement, because whether or not this is allowed depends on the floating point's semantics. Well, this is a straightforward example. There are more subtle examples. For example, here I have two divisions. I replace them with one division and one multiplication. Supposed to be faster. And probably, if this is what you're trying to compute, you might have bitwise different results, but they will be equivalent in the sense of doing the math that your analytical model asks for. Some of the less known examples of strength reduction are these. We saw in the n-body calculation that the power function in the trivial case can be replaced with the square root. And in fact, depending on the floating point semantics, the compiler may make such a replacement automatically. You can actually convince yourself that in the n-body code it does just that. But the reason why this is better is that the power function is probably based on the exponential function with some additional transformations. And this is built in. Knight's Landing processors have AVX512 instructions. And in AVX512, there is a subset called ER, exponential and reciprocal. It contains, among other things, a fast implementation of the reciprocal square root. By the way, not square root, rather reciprocal square root. Square root is slower than the reciprocal square root. When you do exponentials and logarithms, what's implemented in hardware is actually base 2 exponentials and logarithms. So exp2 is actually 2 to power x. Well, exp of x is e to power x. So these expressions are equivalent, and they probably evaluate in the same amount of time. But what they want to show is that sometimes you can simplify your algebraic expressions so that instead of natural base, you use base 2 exponentials. For example, what's happening here, you may recognize if you've done any computer simulations. This is interpolation. I have a function that I know it at 2 points. At x0, the function is equal to y0. At x1, the function is equal to y1. And I'm trying to interpolate between these 2 points to point x, assuming that the function is a power law. Well, many physical quantities behave as power laws, at least locally. So this is often a good approximation. In this expression, it absolutely does not matter for precision which exponential I use. Natural base, base 10, base 2. So there is an equivalent expression that will give you the same kind of, the same accuracy of approximation, but much faster. By the way, this recipe is specific to the Intel Math library. Last time I checked with GCC, I got the opposite result. exp2 was slow, and I think exp2 was even slower. But it may have changed in the most recent versions. That is, I think, for GCC 4.4. Well, here's the promised table. This is the performance of vector instructions in Knight's Landing architecture. Knight's Landing is the architecture of second-generation Intel Xeon 5 processors. For these instructions, I'm listing the latency and the reciprocal throughput. Well, what does that mean? If you're requesting an instruction, square root of x, or 1 over the square root of x, it has a latency in double precision of 7 cycles. So I will have to wait 7 cycles before the result of that vector square root is delivered to me. Takes 7 cycles. But if my program continuously wants to compute square root after square root after square root, and I keep feeding these instructions into the pipeline, then the first instruction will come out after 7 cycles, but after that, instructions will be coming out every other cycle, every 2 cycles. In contrast, if I do simple math like addition, multiplication, fuse, multiply, add, the latency is comparable, 6 cycles, but the throughput is half a cycle. So if I keep feeding these instructions, after 6 cycles, I start getting them 2 per cycle. Compare it, for example, to floating point division and square root. Almost 40 cycles latency and 10 cycles reciprocal throughput. So lower is better for both quantities. Also, pay attention to simple integer math, very fast. Pay attention to division, slow, type conversion, fast. So you need to keep these numbers in mind when you plan for strength reduction. Continuing to talk about programming practices for scalar tuning, I want to mention something that we ran into yesterday. You need to be consistent about the precision of your constants and functions. The rules are simple, but they are often ignored in C and C++. If you have a literal constant in your code that looks like an integer, by default, the compiler interprets it as a 32-bit integer. If you want the compiler to interpret it as 64-bit integer, you need to add the suffix L. This is signed long. If you ignore this, sometimes you can cause overflow. For example, this will not compute. Well, this will result in an overflow, produce incorrect results. This is correct. Also, when you unintentionally mix types in expressions, you may have unintended consequences. Remember how yesterday we had the power function of x and negative 0.5, and x was 32-bit, negative 0.5, as I will explain in a second, is 64-bit. So overload gave us actually a double precision function, which was overkill. Which brings me to the next rule. If you have in your code a literal constant that has a decimal point, by default, by the rules of the C++ language, this is a 64-bit floating point number, so a double. If you want to treat this constant as a 32-bit constant, remember the suffix f. This makes it a 32-bit float. This explains what we saw yesterday. Remember, we had std power of x and negative 1/2. Exp was float. Negative 1/2 was double. So by the rules of the C++ language, I have to promote x to double precision, do the power function in double precision, and then convert the result back to single precision. A lot of unnecessary math, and we had significant speed up when we just put the suffix f here. In addition to controlling the precision of constants, you need to control the precision of functions and also avoid type conversions. What you need to be aware of is if you want single precision functions, add the suffix f. So sine is a double precision function. Sine f is a single precision. There is also some prefixes that you need to be aware of. L around f is actually a function that takes a floating point number, single precision, and returns a long number. And this is my favorite. Abs of x is not the absolute value of x. It expects an integer and returns an integer, so you may cause a bug by doing this. This is the correct single precision absolute value of floating point number. With regards to the suffix f, this is a rule in C, and also the rule in C++ in the global namespace. If you go to namespace std, you can actually enjoy overload. I demonstrated this yesterday, and I wanted to mention this again today. If you look at exp of 1.0f, single precision, exp of 1.0, double precision, you will see that they both return the same result. And this result, if you compare it to the known value of E, is actually accurate to 15 significant figures. So this is a double precision function, no doubt. Similarly, exp, whichever argument you feed into it, will return E with 7 significant figures of precision. So this is clearly a single precision function. If you want overload, if you want the function type to depend on the type of the argument, go to namespace std. And then this will give you a fast single precision function, and that will give you an accurate but slower double precision function. This is the correct result for reference. When you talk about scalar tuning, sometimes what you talk about overlaps with vectorization. And this is actually true for all of these areas of optimization that I listed in that colorful slide. Sometimes what you're doing really touches on multiple building blocks. So in conclusion, I will show you, in conclusion of the scalar tuning discussion, I will show you a couple of good and bad practices that you can view on the scalar tuning level as well as on the vectorization tuning level. So this is an example of a bad code, and this is the same code but optimized on the right. So this is before optimization, and this is after. So what's happening here? I have a loop, and in this loop, I'm handling 2 boundary cases separately, and most of the time, I'm going to run this code. B of I is equal to the weighted sum of AI minus 1, AI, and AI plus 1. This you can recognize probably as a diffusion, a simple diffusion kernel, or a running sum, or heat conductivity stencil, or image blurring. It's all the same mathematics. The difficulty here is with the boundary conditions. When I is equal to 1, A of -1 is not defined. And when I is n minus 1, then A of n is not defined. So how do you handle boundary conditions? For example, on the left, you may have an absorbing boundary. On the right, you may have an injection at the boundary. What do you do about it? In this code on the left, I inserted an if statement inside the loop. I think what this is a good programming practice from the point of view of style, because I'm not repeating myself. In contrast, if you look at it from performance point of view, this is a bad programming practice. Because if this loop is vectorized, what do you do about vector loops with if statements inside? I think I explained it in session 3. What you do is masking. So the compiler will have to implement code that always computes this for every value of I. It always computes that for every value of I, and it always computes this for every value of I. And then it does masking to preserve the correct output. So on the level of vectorization, this is inefficient. And also on the level of scalar code, you can see that it is inefficient, because for every value of I evaluate the branch, but most of the time I take this branch. So both from the point of view of scalar and vector tuning, you are better off rewriting this code, isolating boundary conditions outside, and changing the loop bounds so that you have no masking and no branch evaluation in the code. Let me show you a more dramatic example of that. And this really is the conflict between good style and good performance. What we see here is a strip-mined code. Originally, we had a code where I was going from 0 to n. But then, maybe for the purposes of exposing vectorization opportunity, we strip-mined it. So the outer loop goes with a stride of 16, and the inner loop performs 16 iterations inside. This is all good, as long as n is a multiple of 16. If n is not a multiple of 16, we may have a problem. For example, suppose that n is equal to 40. So 0, 40. Then we have 16. We have 32. And the first loop will process these iterations. The second loop will process those iterations. And the third loop, if we didn't have the branch, would hit the array out of bounds. So to protect ourselves, we could just insert this branch if I is less than n. This is elegant. Minimal change to the code, no repeating yourself. It just works. My claim is that it's bad for performance. Well, again, because we have a branch inside. And you are better off writing a remainder loop. And this, in fact, is what the compiler will do every time you have a loop with where the number of iterations is not known at compile time. So I'm introducing n truncated, which is n minus n modulo 16. In the case where n is 40, it would result in n truncated to be equal to 32. Then we do the strip mine loop, and we don't need to protect this because we will not overshoot the array bounds. At the end of this loop, we write a remainder loop, and it's going to be processed. It's only going to have 8 iterations, maybe scalar, maybe masked vector. This is okay, but think about it. This is bad programming style. I'm repeating myself. This is just one line of code, but what if the body of this loop was 20 lines of code? I would have to copy these 20 lines of code here. So bad programming style, but good for performance. And it doesn't depend on the architecture, doesn't depend on the compiler, just the nature of vector instructions. So keep this in mind. Sometimes you want to repeat yourself just to avoid overly complicated calculations inside scalar or vector loops. Well, that's what I had regarding scalar tuning. And I also have some information regarding vectorization. We talked about vectorization in session 3, but as I said there, when you see loop was vectorized, this is only half of the success. Full success is when you don't just get vectorization, but also make it efficient by taking care of any red flags in the optimization report. You already saw this in action yesterday. We vectorized the code, but then we saw non-unistride access. We fixed it, but we saw peeling. And today, we are going to talk about this in more detail. Reminder for everyone, vector instructions implement single instruction multiple data, or SIMD parallelism. It means that you can take multiple numbers at once, load them into a vector register. If you have multiple operands, load the other operands in a vector register, and then apply one instruction that will be computed element by element in every lane of that vector. The idea is that hardware for this math is replicated inside the chip. So the latency and the throughput of these vector instructions will be the same as the latency and throughput of just a single vector instruction. And potentially, vectorization can speed up your calculation by a factor equal to the length of the vector. The compiler will often vectorize scalar loops by detecting opportunities for data parallelism. But you, as the programmer, are responsible for preparing code for vectorization so that vectorization is efficient. Particularly, you need to worry about memory access. There's two aspects to memory access. It needs to be local in space, and it needs to be local in time. Time locality we will discuss later, but let's focus on locality in space. Ideally, when your loop goes through some data in arrays, you want unit stride access. This is an example of unit stride access. I increment I by 1, I move in memory to the next adjacent element. This is efficient, and this is what you should always try to achieve. It is also possible to vectorize calculations that have non-unit stride. For example, if I is multiplied by some stride, which is an integer greater than 1, then we have a scatter operation. If stride was in the right-hand side, we have a gather operation. The compiler will vectorize loops like this, but it will be slower. We saw an example in the n-byte calculation when we used an array of structures, and we had to load several consecutive values of coordinate x. We had to read every sixth element. Well, in this picture, it's every third element, but in the code, it was every sixth. This was inefficient. We optimized it by changing the data structure. It was a lot of work, but we ended up with unit stride access. And on Z1 on KNC, the speedup was a factor of 5, and on KNL, the speedup was a factor of 3. Very significant. You should also be aware that if you have indirect access, where offset is in general a stochastic function of I, this is going to be even less efficient. In fact, if the offset can be expressed as an expression, something like this, you are better off doing that than hiding the offset into an array. But if it's possible to reorganize data, maybe do that. I will not demonstrate this optimization live today because we spent a great deal of time on it yesterday. If you want to practice some more, pay attention to lab 402, and you can read instructions and perform it at home yourself. It will guide you through some steps where you do the AOS to SOA conversion. When you have vectorized loops, in addition to unit stride, you may also think about data alignment and about padding multidimensional data containers. Alignment is a property of a memory address. You can say that a memory address is aligned if the value of this numerical address is a multiple of the alignment value. For example, if you have a memory address that is a multiple of 64 bytes, this is a 64-byte aligned memory address. Why do you need to worry about alignment? Alignment, most of the time, is important for loading and storing data from memory into vector registers. You will also see cases where alignment is needed to avoid false sharing, and you may need to know that when you do communication in a cluster or communication with a Z1 coprocessor, sometimes you want to do alignment to accelerate remote direct memory access. How much you need to align really depends on the architecture that you're running on. If you're using an older Z1 processor and you have SSE instructions, you need to align data on 16 bytes. For more recent processors, which support AVX instructions, they like 32-byte alignment, but alignment requirements are relaxed. So if you don't align, you can still load and store. It just is slightly slower. If you are working with an Intel Xeon Phi processor KNC architecture, it wants 64-byte alignment, and this is a strict requirement. You cannot load from a non-aligned address. The same processor, if you want to accelerate offload, align on 4 kilobytes. But back to vectorization, Knight's Landing processors want 64-byte alignment, and again, this is a relaxed requirement. And at this point, you can say, wait a second. Didn't we just vectorize loops without worrying about alignment? And the answer is yes, and I will show you how, and I will show you that you still want to align. So this is why. If you're vectorizing a loop where you access some data structure, ideally you want this data structure to begin on a boundary that is aligned, for example, in 64 bytes. This way, your first vector iteration is fast because you load from aligned memory addresses. The next vector iteration is fast, and so on. And you want to finish your loop with a full vector iteration. This is the ideal scenario. So what if you did not take care of alignment and your data starts a few positions away from an aligned boundary? The compiler knows about it, and a good compiler, particularly the Intel compiler, will peel your loops. Peeling means that the compiler will split off a few iterations. Not the compiler, but the code at runtime will be able to split off a few iterations at the beginning of the loop and process them separately. It will incur some overhead because you will have to do masking, but you will reach a boundary that is aligned. And from this point on, you can go with fast vector instructions. If at the end you have an incomplete vector instruction, then you will run a remainder loop. So good compilers know how to implement code like this, general code, and usually when you do automatic vectorization, it will just happen and you don't need to worry about it. But if your loops are short, if you just have a few iterations here, then loop peeling is actually overhead for you. And you may want to reduce this overhead or eliminate this overhead by shifting your data container so that you don't need peeling at runtime. I will show you a case today where shifting the data container is not possible. In this case, you may want to pad your loops so that, well, physically you need to crunch this data, but you will start the loop sooner, and you will crunch some garbage data just to make sure that your first vector iteration is full and you don't need masking. Okay, so you're motivated to align. How do you do that? If you're using C and C++ and your array is on the stack, you can use the attribute align64. Intel compilers understand it, and also GNU compilers starting from version, I believe, 4.9 will understand the syntax. This is an extension to the C++ language, or C. In Fortran, you can force alignment only for allocatable arrays. And for that, you will use a directive. I cannot give you off the top of my head the syntax, but it's easy to find in the compiler reference. Back to C and C++. If you're aligning an array that you place on the heap, then instead of malloc, use a special allocator. There are a few special allocators. I like mmmalloc, which takes two arguments: the size of the buffer that you want and the alignment of the beginning of that buffer. When you do that, a of 0 will have an address that is a multiple of 64 bytes. You don't want to align on very high boundaries because you may waste virtual memory. And you don't want to align every single variable. You only want to align arrays. Scalars, no need. So in Fortran, you have a directive for allocatable arrays, or alternatively, you can actually use a compiler argument that will align all arrays above a certain size. That's easy, but it is a little bit more tricky when your containers are multidimensional. I often see functions, particularly all of BLAS functions and all of laypack functions, I believe, store matrices in one-dimensional containers. So I have a matrix A. It is a matrix of size n by n, and I will store it in a one-dimensional array of size n by n so that I can address elements like this, A of I times n plus j. When you do that, if you have alignment sensitive loops, then in addition to alignment, you also want to pad the inner dimension of your container. So that's why. Suppose n is equal to 40. And you're running it on Xeon Phi. Xeon Phi wants 64-byte alignment. 64 bytes in single precision is 16 floating point numbers. So 40 is the good alignment value times 2 plus some odd numbers. Okay, so what's going to happen here? When we just begin the loop, I is equal to 0, you begin this loop at j0, you're aligned. When I is equal to 1, you begin 32 bytes away from an aligned boundary, so you're not aligned. I equal to 2, aligned, and so on. This is unsatisfactory because every other time you will do loop peeling, which is overhead, and every time you run this loop, you will have to do a check. Do I need to align? Do I need to peel? Do I need to peel? Do I need to peel? And so on. So it is good practice if you do things like this to choose a slightly bigger inner dimension than you need to make sure that you have alignment. For example, if you plug in the numbers, for n equals 40, L leading dimension of A will become 48, which is 16 times 3. And when you do that, for every value of I equals 0, you're aligned. I equals 1, you're aligned. I equals 2, you're aligned, and so on. So these measures you can take as the programmer to make sure that at runtime you never peel. And that makes sense. I will show you today how this is done and what performance you can expect. When you've taken all of these measures, the code will be happy at runtime, but the compiler may not be able to detect that you've guaranteed alignment. So it will still implement the check for peeling, and it will still put the peel loop in your code. It will never be taken, but it will sit there, blow up your code, and the check will take some time when you begin the loop. You can actually remove this check by promising to the compiler that alignment has been taken care of. You do this by using the directive pragma vector aligned. You put it before a loop, and what happens is the compiler is forced not to implement a peel loop. This is good and because it can lead to significant speedups. And it makes sense to do when you know that alignment is there. If you make this promise, but at runtime you actually don't have alignment, then depending on the architecture, you may either experience a slowdown or your code may even crash. As an example, I will use LU decomposition, and this will be our hands-on exercise. So I will go through this math in a second, but let me leave detailed explanations for the second hour of the webinar. We will take an example and we will see how we can guarantee alignment, how we can how we can pad loop dimensions for that, and how we can drop unnecessary checks with compiler directives. You will see that it results in significant speedups, I will also illustrate memory optimization. But to conclude the theoretical part of the code, of the presentation, I want to discuss the last technique for optimizing vector calculations, and that is strip mining. Is it the last technique? Sorry. Yes, it is. So strip mining, we already saw in action, and this is a programming technique that turns one loop into two nested loops. Usually, strip mining is used to expose vectorization opportunities. So you will use strip mining in cases when the compiler is unable to automatically vectorize loops. Strip mining in general looks like this. I have a loop that goes in I from 0 to n. I rewrite it as two nested loops, one going from 0 to n with a stride that I choose. This is a tuning parameter. And the other loop goes from one outer index to the next outer index. If n is a multiple of the strip width, I have no problems. If it is not a multiple of the strip width, as I showed earlier, you may want to choose a slightly smaller upper bound so that you don't have to insert if statements here. And this will require that you write a remainder loop to execute all of your iterations. The advantage here is that you get a separate loop. For example, if the compiler wasn't able to vectorize and parallelize the loop at the same time, now you have two nested loops, and you can apply an OpenMP directive here to parallelize this loop across threads, and you can apply vectorization directives here to guide the compiler with regards to automatic vectorization. I will also show you a case in the hands-on exercise part where strip mining is used as a preparation for loop splitting. For example, your code may have some vectorizable code and some non-vectorizable. When this happens, what you will have to do is you will have to split vectorizable code from non-vectorizable code to run them separately. But if you split this loop into two, you will need to carry some data from one instance of this loop to another. This is inefficient, and strip mining may help you to optimize it by reducing the loop length. I will illustrate with an example that uses binning, and we will compute a histogram. It is actually a representation of a more general class of problems, such as Monte Carlo calculations. Today we talked about optimization of scalar and vector calculations. The primary takeaways are vector-friendly structures, data alignment and padding to regularize the vectorization pattern, removing runtime checks for alignment with compiler hints, and strip mining in cases when you cannot vectorize. I have two very interesting labs planned, one LU decomposition and another on binning, where we will see the optimization of vector calculations in action. Let's do this after a break. And the break, as usual, will be 5 minutes. If you have any questions, feel free to post in the chat here. Muting my microphone, talk to you in 5 minutes. Well, as promised, two entertaining demonstrations coming up. In the first one, we will see how fine-tuning vectorization can lead to performance benefits. We will use as an example the LU decomposition algorithm. LU decomposition is a standard operation in linear algebra. It takes a non-degenerate matrix A and represents it as the product of two matrices, L and U. The idea is that L is a lower triangular matrix, and U is an upper triangular matrix, meaning that in L, all elements below the main diagonal are non-zero, above the main diagonal 0. In U, also only above the diagonal you have non-zero elements, and on top of that, on the diagonal, you have ones. LU decomposition is not unique, and there are many algorithms for obtaining it. We are going to apply the Doolittle algorithm, named after its inventor, which is essentially based on Gaussian elimination. This is the algorithm. The way that it works is it has three nested loops, one in B, one in I, one in J. I'm going to take matrix A and I'm going to take B equals 0, meaning that I will take the top row of the matrix. Then I will take this row, multiply by a certain number, such number that when I add this row to row 1, I will get a 0 below the main diagonal. Then I will multiply it by some number to get a 0 in the second row, multiply by 0 to get a 0 in the third row, and so on, until I get zeros everywhere in the first column, in column 0. So what I'm saying is that I is going to range from 1 to n, when b is equal to 0. J in this algorithm just enumerates columns. J goes from b plus 1 to n. The interesting thing is that when I do that, I will get matrix U above the main diagonal. Yeah, so I do that, then I choose b equals 1, meaning that I take this row, multiply it by a number, get a 0 here, 0, 0, 0. Then I do b equals 2, take this row, add to the subsequent rows, get zeros. So I will naturally get a unit triangular matrix above the main diagonal. But if I also store the coefficients by which I multiply these rows to the left of the main diagonal, I will actually get L right here. You can verify that. We are going to see what is inefficient about this calculation and how to deal with it. Actually, let's take a look at it while we have the code up right here. The loop that's target for vectorization is this one, because it is the innermost loop. And this is not such a bad idea. J gives us unistride here. This is a constant. This is unistride. So no gathers or scatters. Unistride, const, unistride. But look where J begins. By the nature of the algorithm, it has to begin at b plus 1. And b will take all values, 0, 1, 2, 3, and so on. So if I want alignment, well, I could align A. I could pad the value of n so that it is a multiple of the alignment value. But I will still begin this loop on unaligned boundaries 15 times out of 16. That's because j keeps starting from a new value every time. So the pattern with which I traverse this matrix is like this. This is the main diagonal. I go like this, like this, like this, like this, like this. This is a nightmare for vectorization because I almost always have a peel loop, and the length of this peel loop is different every time. So my idea is to change the vectorization pattern so that I will go from the correct position if I'm aligned. If not, I will actually begin sooner. So I will do this. Then the next one actually begins on a boundary that is aligned, so I will do that. But then I will keep crunching garbage. So see, I'm adding the processing of these values below the main diagonal, which is dangerous. It may change my results. I will resolve this problem by separating L and U, and you will see that it actually makes sense in terms of performance. Well, I promised a practical exercise, so here it is. I am on the cluster, and when you log in, you can go to the House Series Labs, enter chapter 4, and in chapter 4, go to 403. In 403, I have main.cc, and right on top, it has the algorithm that I want to apply to my code. You can see that it's slightly different from what I showed, because I already separated L and U on output. Usually, if you go to laypack definitely has LU decomposition. The assumption is that you feed in A, and on output you get L and U in the body of A. That's fine, but just to make it a little bit clearer, and I could of course do that, but to make it a little clearer, what I do is I assume that my function takes A on input, and on output it returns U in the body of A, and it returns L as a separate matrix. So this is input and output, and this is only output. So this is my function I will be working here. I want to point out that this function is single-threaded, right? No OpenMP pragmas. But my code is actually parallel, because I'm assuming that I'm transforming small matrices. N is only 128. It's difficult, because the loops are so short. But the saving grace is that I have many of these matrices that I need to transform, to decompose. I have 10,000 matrices. So I have an array that has one matrix after another matrix after another matrix after another matrix, and there's data inside. And what I'm doing is, when I run, I throw one thread per matrix on the problem. This thread is done, I assign it to a different matrix, and so on. I do this with OpenMP, and it looks like this. This is the code that I'm timing. See, I'm iterating over matrices. For each matrix, I call LU decomposition. So one thread per matrix, and one matrix per thread. So my code is going to use all cores, and I'm going to evaluate the cumulative performance of all cores, but the code of LU decomposition itself is single-threaded. This may not be the best way to process this problem, but it is certainly good for illustrating optimization of vector calculations. Compile. Submit to the queue. And while it's running, I will prepare, as usual, a log file. So what's happening with the original code? Okay, so here is my performance. The CPU gives me 155 gigaflops per second. Xeon Phi gives me 190. 90. That's the old Night Corner coprocessor. Night's Landing processor gives me 194 gigaflops per second. Well, that's good, but I would like to at least get more performance out of my Night Corner than the Xeon. So I may need to optimize. In my optimization report, it actually looks optimistic. And I look for line 17. It's all good. So there's peeling, and there's multiversioning, but the loop was vectorized. So that's not bad. The peeling, as I explained, is the problem, because most of the time it will be taken. And my loop is only 120, well, n is only 128. So on average, so at most, 128 by 16, 8 vector iterations. On average, 4, of which 1 is peeled, masked. This sounds like a very high overhead, so I may be better off doing this padding of row dimensions, as I explained. To pad the row dimensions, what I will do is I will change the beginning of this loop. Instead of p, I will start it at jmin, where jmin is what? I want to choose jmin so that jmin is a multiple of 16 and jmin is less than or equal to b. Let's see how this is done. Jmin const int jmin is b minus b modulo 16, I think, like this. So what does that do? That compiles. Let's run and record the performance results. I think it should improve performance because we will not take the peel loop. Of course, I need to be careful because I'm overwriting some elements in A. But it's okay because, as I explained, when I return the results, elements below the main diagonal in A are irrelevant. They are not used. I could potentially copy the matrix A, the matrix L into matrix A at the end, but I don't want to confuse everyone. So, a log. I replaced b plus 1 with jmin. What did I get? Uh-oh, that doesn't look so good. 44 gigaflops per second on the CPU, 18 gigaflops per second on Night Corner, and 40 gigaflops per second on Xeon Phi. So performance went down. Why that happened, we can learn in the optimization report. So our loop is now in line 19, and let's see what the optimization report has for line 19. Multiversion version 1. Loop not vectorized because of loop dependence between in line 20. Multiversion 1. And then actually multiversion 2 is also not vectorized. That's not good. So what's line 20? Line 20 is this line. And what happens here is the compiler doesn't know. Now that j is some abstract value j min, what if j min is negative? We know that I is always greater than b. But if j min is negative, then could we potentially be overwriting some of the earlier values of I here? I think that's the situation. So the compiler doesn't know if it's safe to run this loop with vectors or not. Well, after session 3, we know how to override this, and there is a directive, pragma omp simd. It tells the compiler to definitely vectorize this loop. Recompile, check the vectorization report. The loop is now on line 20. Well, that's better. The loop is vectorized, peeled and vectorized, and there's also a remainder loop. Well, looks good. What will performance give us? Submitting. So pragma omp simd. It forces loop vectorization when the compiler has doubts. Okay, finalizing. Takes a long time to finalize for some reason. Okay, so the last 3 performance results is what we got now. And this looks much better. The CPU gave me 159, slightly better. Knight's Corner gave me 105. So 15% performance boost. On Knight's Landing even more, 257. On Knight's Landing it's more like 25-30% performance boost. 30%. So I'll take it. But if I want to keep going, now I have to recognize that in the code, I guaranteed that I'm always aligned. But the compiler is unable to determine that. So the compiler still implements loop peeling. See this? And I can potentially get rid of it by inserting a directive, and you're familiar with this directive already. Pragma vector aligned. What I expect this to do is to get rid of the peel loop in the executable. Let's check. The loop is now in line 21. And yes, indeed, I have the CMD loop vectorized, and I have the remainder loop vectorized. I cannot get rid of the remainder loop, but it is usually harmless because branch prediction takes care of it. That's what I've been told. So what I did is pragma vector aligned. And my last 3 performance results show me that, yep, it makes a little bit of sense. 159. 115, and 269 gigaflops per second. Well, we did optimize the nature of vector calculations, the pattern of vectorization. It required 3 steps. Step 1, we replaced b plus 1 with j-min. Step 2, because we lost vectorization, we recovered it with pragma OMP SIMD. And finally, step 3, we eliminated the p loop. The motivation for all that was to get rid of the p loop. Let me illustrate something that would have happened if we were impatient. So the code looked like this when we touched it, when we first touched it. We didn't have any of this. Right? We just started with b plus 1. What if we just looked, there's a p loop, let's kill it, and inserted pragma vector aligned? Well, what would have happened is, indeed, the compiler would eliminate the p loop. So the loop is in line 23. Well, there's still multi-versioning, but there's just the main loop and no peeling. So did we really have to go into all this trouble? Did we really have to introduce jmin? Did we have to do pragma OMP SIMD? Couldn't we just get away with this? The results will speak for themselves. So, something happened. Looks like I have an error in correctness checker. I think that's because I should have put b here and not b plus 1. Is that right? But, okay, that's just a bug. But I think we will learn even more from KNC. KNC printed nothing at all. And I think it's difficult to troubleshoot, but on KNC, we actually had a segmentation fault. That is because 64-byte alignment is required by the architecture. So it shows you what happens when you promise alignment, but you do not deliver on this promise. You can have crashes. Okay, well, let me recover the optimized code for your reference and take another critical look at it. We saw loop was vectorized. This is all optimistic. Maybe the compiler report can give us some more clues. So let's request a more detailed optimization report. Instead of qopt report, I will request qopt report equals 5. So recompiling. And let's see what we have for the loop in line 21. Loop in line 21. Aligned access, that's good. Vector length 16, unroll. Unmasked aligned unit stride loads. Yep, nothing exciting, to be honest. There's an interesting remark about a suggestion for loop interchange. It wasn't possible to do this automatically, but indeed that might improve our memory access pattern, but it's tricky. I was hoping that the compiler would suggest something for this line, but it didn't, because it was not vectorized. So let me try it myself. As you can see, I keep dividing by ABB. And I do it how many times? On up to 128 times. On average, 64. So even though I have another loop inside here, that loop uses just a few vector instructions. So one expensive scalar operation may actually overshadow those vector calculations. So what I'll try to do is, instead of dividing over and over, I will actually multiply 1 by 1 over ABB, where 1 over ABB I will compute outside the loop. 1 over ABB is the reciprocal of AB. It will slightly change my results, and it might reduce accuracy. It may degrade accuracy. But if I don't care that much about accuracy, maybe I can pull this off. Recompile. And do what? So I replace division with multiplication by the reciprocal value. Well, the last three values are these, and I think they prove that it made sense. So I have 162. On the CPU. Knight's Corner gives me 137. And Knight's Landing gives me 277. So overall, what we did is not so bad. On the Xeon, we just gained a few percent, but on Knight's Corner, we gained 50%. On Knight's Landing, also of order 50%. So it makes sense to consider data alignment, and you need to be careful. Pad the inner dimension of multidimensional arrays, possibly pad the loop bounds, and when you have taken care of alignment, use the directive pragma vector aligned. It only matters when your loops are relatively short, because if your loops are long, then the overhead of the P loop is negligible, and you don't need to worry about this. At the same time, what we ended up with is not so satisfactory. This on Xeon Phi is lower than the performance of the same code on the Ivy Bridge processor. And I did these tests offline, and I got the same results. This is what I did. Knight's Landing is winning, but Knight's Corner should be slightly better, but it's not. And this boils down to the last remark that I made in session 3. In order to make vectorization shine, you have to optimize memory access. That is because memory access in modern architectures is expensive. vector floating point math is cheap. You can see that I can make one more step that will really make the Xeon Phi, the Knight's Landing performance jump. It will also reflect positively on the Xeon and on the Xeon Phi. Xeon Phi first generation Knight's Corner is not going to beat the Xeon by a large factor because this is a complex problem, and this may not be the end of the route for memory traffic tuning. But you can see how important this is. You can fine-tune vectorization all day long, but at the end of the day, if your data is coming from the main memory inefficiently, you're missing caches a lot, you are not going to get satisfactory results. In our case, it is indeed non-trivial. So our matrix is n by n, where n is 128. So this is 227 times 227 times 4 bytes. This is 2 to 16, 64 kilobytes. And we have, in the case of Xeon Phi, 4 such matrices per core. So we have 256 kilobyte per core. This fits into the level 2 cache, but it is greater than the level 1 cache. So we need to be careful about data reuse. I do not want to go through the steps of this optimization because it is non-trivial. This is a complex algorithm. It has some sequentiality in it. So instead, you can just go to instructions, instructional 4, and see what the optimized code looks like. This is just one of the approaches, but it works. It uses tiling. We will talk more about tiling in session 10. And you can see that the code is a lot longer. It repeats itself a lot. But the key idea is that the innermost loop, I want it to be either short or I want some data reuse inside of it. So what this is the optimization of data access locality in time. When I talked about unit stride access, I said that this is the optimization of that unit stride is the optimization of data access locality in space. This is the optimization of data access locality in time. If I used some data, I want to reuse it as soon as possible while it is still in caches. You can also go and test out the performance of this code. Easy enough. Just go to solutions, instruction 04, queue everything. And then the CPU will give you 234. Knight's Corner gives you 232. And Knight's Landing 649 or 469. Another storyline that appears here is this. See how we started? Suppose we didn't have KNL and we just were comparing the Xeon to Knight's Corner. We test our code and Xeon Phi works poorly. It's not well optimized. Then we start optimizing, and oh, finally, Xeon Phi gives me a better result than initially I got on the Xeon. And it can be, well, in this case, this is a factor of 1.5. Sometimes it's a factor of 100. And it's of course tempting to jump and joy, but you have to remember that we are developing portable code. So the optimized code that you have on Knight's Corner should work well on Xeon. And indeed, when you run on Xeon, well, KNC is way up there, but so is Xeon thanks to the optimizations that he did. So looks like we are learning useful techniques. Hopefully I've convinced you of that. Well, this is what I wanted to demonstrate in this part of the hands-on exercise, LU decomposition. If you have any questions, feel free to post in the chat. And in the meantime, I will move on to the next exercise. The next exercise will demonstrate strip mining. Strip mining is a programming technique that you need to apply to expose vectorization opportunities. Usually, this is done to expose vectorization opportunities, but it has some other applications too. I've shown you what strip mining looks like in the lecture part, and I will now illustrate it using an example. For the example code, we are going to use binning, the binning problem. Well, this is the code that we're going to optimize. Whew, just 3 lines. But it will be fun. We have a large array, 100 million elements, and it contains the ages of 100 million people. So this person is 56 years old, this is 52, 21, 46, and so on. We're assuming that they are all contained between 0 and 100. If we have somebody older than 100 years old, we process them separately. Our goal is to compute how many people I have in the age group from 0 to 20 years, and how many people I have in the age group 20 to 40 years, how many people in the age group 40 to 60, 60 to 80, 80 to 100, right? Easy to do, right? We take the age of this person, divide by the group width. The group width is 20 years. We get a number, which we have to round down to an integer. And this gives us the age group number. So this is age group number 0, 1, 2, 3, 4. This person is 56.8 years old. They map to group 2. So I have to go to my histogram container, and I have to increment this counter. Looks correct. Encode age divided by group width, round to an integer, get j. Substitute this j here, increment this counter. I only have 5 age groups. Of course, this is a limited example, and if we really have such data, we probably don't want to optimize it too much because, well, maybe we just need to do it once. But if it's something that we do repeatedly, for example, in a Monte Carlo calculation, then we might as well optimize this workload. Now, we are focusing on vectorization, and this is what we will be on the lookout for. This lab is found in lab 4, this workload in lab 4, and there I want you to open worker.cc. This file contains just the function that we are going to optimize. And we are operating here. So let's obtain a baseline. And while calculations are running, I want to create a log file as usual. So Xeon, Ivy Bridge, Xeon Phi, Knight's Corner, and Xeon Phi, Knight's Landing. Original code. Done, almost. Takes a while on Knight's Corner. Well, while it's computing, let's do something useful and look inside the optimization report. The only loop that we have in our calculation is in line 12, so this is what we are going to look for. It was peeled, and it was vectorized. Ah, not bad. Just in case, let's check what happened with Knight's Corner. Oh, on Knight's Corner, the loop was not vectorized. On the CPU, same story. The loop was not vectorized. This is because of this line, line 18. And the problem here is that this is not really a data parallel operation. We are vectorizing by gluing together several values of I. And then for several values of I, we load several ages into a vector register. We divide this vector register by another vector register containing the group width. And we get a vector register, well, we round it to an integer, convert it to an integer, we get a vector register full of J's. And then we use this J to jump to a certain memory location. And this is not data parallel. We may well have the same value of J for different values of I. And this means that we may have conflicts. So this is not a vectorizable operation. Interestingly, on Knight's Landing, they introduced a special instruction dataset module, AVX512CD. CD stands for conflict detection. And it is specifically designed for computing histograms like this. So this operation, Knight's Landing knows how to vectorize. Knight's Corner and Ivy Bridge, they don't. So if we want portable code, we will need to transform this code so that it vectorizes, but we don't want to tie it to a particular architecture. Well, baseline is there. And we are doing lab 404. So this is our performance results. Oh, on Knight's Corner, it actually crashed because it ran out of time. So Xeon gives me 3.8 times 10 to 8 values per second. This is the metric, so higher is better. Knight's Corner gives me, I'll know in a minute, Knight's Landing gives me 1.2 times 10 to 8. To see Knight's Corner results, I probably have to do this. KMC. Yeah, it made a few iterations and then it ran out of time. 1.9 times 10 to 7. Well, it's not surprising that Xeon Phis give me poor performance. If you look in the main code, it's actually not parallelized. So this is serial code, single-threaded. And in fact, tomorrow we will take this code and play with it so that it becomes multi-threaded. But for now, we will take what we get. I wrote this down incorrectly. This is it. But still, we want to get the most that we can from one thread on KNC and on Ivy Bridge. And for that, we would need to vectorize our code. To vectorize our code, we need to recognize that this part of the calculation, it is expensive, but vectorizable. This part is inexpensive, but it has to be run with scalar instructions. So my best idea is to split vectorizable calculations from non-vectorizable calculations like this. Beautiful. The first loop now I can vectorize. The second loop, well, so be it. Well, this code, of course, will not compile because I'm computing J. I'm immediately forgetting it and moving on. So where does J come from here? I have to to somehow pass j's from one loop into the other. So the best I can do is maybe to create an array of j's, size n, and here I will have j of I, and here I will have hist of j of I. This compiles, and even more importantly, on the CPU and on KNC, it vectorizes the first part of the calculation. The second part cannot be vectorized, but we will have to live with it. Well, this is not a bad idea, but if I run it, I will actually have a segmentation fault, because n is 100 million. Too large for stack. So now I have the option of blowing up my stack to be unlimited, or alternatively allocating it on the heap, which means that I either have to modify my code and allocate scratch space outside this function, or I have to touch the heap from a computational function. I don't like either of these. And most importantly, look, we used to be dealing with a large array in the hundreds of megabytes. Now we have two large arrays of the same size. And instead of reading this array once, we read this array once, then we write this array once, and then we read this array one more time. So we tripled the memory traffic. So I don't even want to go into the trouble of benchmarking any of that. But I want to capitalize on this beautiful idea of loop splitting. Sorry for self-advertisement. This is where strip mining will help. So that we don't have to carry that much data from one loop to another, let's make this loop short. And that's how we will do this. We will rewrite this code as two nested loops. One will go from 0 to n with a stride of something that I will have to tune. For lack of better knowledge, I will call it tile, and this will be equal to 16. Then the inner loop will go from II to the next value of II with a stride of 1. Well, let's imagine that tile is 16. Now, if I split the loops, I don't have to waste that much memory. Because, look, I have to carry how many elements? Just 16, right? I have to take these 16 elements and put them here. Then reuse the same array, put it there. They can comfortably live in registers, and I will never have to go to memory. So instead of j of n, now I can have j of tile. And of course I'll have to tweak this. This has to be I minus II, and the same thing here. But I think I will achieve both goals. I will vectorize, and I will avoid blowing up the memory access pattern. So the loop we're looking for is in line 16. It was vectorized. The loop in line 22 was not vectorized, but so be it. This is not a vectorizable calculation. So what we did is strip mining and loop splitting. Now, the last three values are, did I lose one? This. Let's make it a little bigger. Even bigger. Okay, so the CPU gives me 6.9 times 10 to 8. The Knight's Corner gives me 1.0 times 10 to 8. And Knight's Landing 1.24 times 10 to 8. Well, on Knight's Landing, performance didn't change because the code was vectorized in the first place. But this is 5x, this is almost 2x. Not bad, so we will live with it. And before we finish, I want to take a critical look again and see if anything burns my eyes. And something does. This is a statistical calculation, so we are not that sensitive to performance. And we keep dividing by 20. I don't like this, and I will instead do multiplication by 1 over group width, where the group width I will pre-compute. Yes, it will slightly change our results, but it should be perfectly acceptable in a statistical calculation. So resubmitting, and I should see correct results if I did it right. And the performance should be slightly better. So this is another example of scalar tuning. So division replaced with multiplication. And this is the last point that we will mark today, 8.8 times 10 to 8. As you can see, the compiler did not do this automatically. 1.5 times 10 to 8 and 1.5 times 10 to 8. I did this at home as well, and this is what I got. We started here, we did strength reduction and vectorization. On all platforms, performance went up. Xeon Phi is still way behind the CPU. The numbers are obtained here are, I think, from an older compiler and also from a different system, so they are slightly different. But the bottom line there is that there is a big gap between the CPU, which is doing well, and Xeon Phi, which is not doing so well. And that is because even though we did vectorization, we need more work to do. And that is because we have yet to take advantage of multiple cores. And we will do this tomorrow. This is a very convenient exercise for learning. We will start where we left off tomorrow and address two more issues. Parallel reduction and false sharing. So for tomorrow, we will talk about reduction, false sharing, insufficient parallelism, plus we will discuss loop scheduling. If you have any further questions, please don't be shy to ask them in the chat. The chat is at the very bottom of the course webpage, and we're monitoring this chat. Hope to see everyone again tomorrow to talk about another aspect of optimization, thread parallelism from the point of view of commonly encountered issues. Have a good rest of the day, everyone. Goodbye.